All right, welcome back. So this is going to be our limits video number 2. And so I'm still on the day 1 worksheet, just trucking along a little bit here. And so now let's enter into part 2. So in part 2, we have a definition of a limit. Okay, I would like you to think about everything you've done so far this school year with the Desmos activity and then our introduction. How would you define a limit? So I want you to pause the video, write down what you think the definition should be, and then come back. Okay. All right. So a limit. I'm hoping that you mentioned something in your definition that as x gets closer and closer and closer to some value, some arbitrary value, the limit would be what is the output getting closer and closer to. If you were able to say something along those lines, or you were thinking something along that, then you're on the right track, okay? So we just want to formalize it. So a limit is if f of x becomes arbitrarily close. Oh, I gotta make sure I'm spelling this right. Arbitrary, that is not R-I-L-Y. Whew. Close to a unique number, and I'm calling this number L, as x approaches some value from either side the limit of f of x as x approaches that number is L. Okay, the notation looks like this. Okay, so let's pull this apart and make sure that we're understanding what the heck am I writing on the board. Okay, so if f of x becomes arbitrarily close to a unique number L. Okay, so what we're talking about here, this means output, right? So if the output becomes closer and closer and closer to this, okay, so this is still output. Well, okay, let's keep going. As the output becomes really close to a unique number, it is extremely important that we're saying a unique number. A unique number means one specific number. You've heard me say this throughout the year. I was getting you ready for this. I can't have multiple unique numbers, then it's not unique. Unique means a single value. So if the output becomes arbitrarily close to a specific single number, as x is approaching something from either side. So in the example we just looked at with the area, it was as x approached 8 from the left, as x approached 8 from the right, then we got a limit of 64, okay? So it's really important that we're looking at these key things. We need a unique output, okay? And we're also talking about as x is getting closer and closer to something, okay, from either side of it. So as we look at the left side of a number, as we look at the right side of a number, are we getting closer and closer to a unique output number? Then the limit exists. And we've joked around in class about that sometimes the limit does not exist because we have a function that's not approaching a single unique value. Okay? So if this is not clear to you, please, please, please send me an email. Send me a question on Remind, and I can expand on this. Okay? We can also find this in your book, and we can read and take notes as necessary. Okay? So with that, let's take a look at some of the examples on this page. Okay? We're not going to do all of them together because I want you to practice, but we're going to look at finding the limit in a few different ways. We can find it from a table or from a graph, and that should make sense because a table gives us a graph, right? Okay, so let's take a look at the very first example, which is the limit as x approaches 3 on 5x minus 3. I would have your calculator handy, okay, to help us out with this. Because at this point, Sorry about that. At this point, I'm not expecting you to do these without a calculator. That's going to come in maybe like another 2 lessons. But for right now, let's just get used to this. So as our limit as x approaches 3 on 5x minus 3. Okay, pause the video. Try the problem. Can you get it? Okay? All right, so if you pause the video and you want to know if you're right, the answer should be 12. Okay? So you could potentially fast forward this for a little bit. All right, so I want you to do this in 2 different ways. I want you to look at a table of values, and I also want you to actually physically graph it. Okay? So your table versus your graph. Okay, now I'm going to hope we don't actually need a graphing calculator to graph this, but I did say go ahead and use one. I don't have my graphing calculator right in front of me, so I'm going to look at doing this by hand. Okay? So we've got a 5x minus 3. That means that I have a y-intercept of -3, slope of 5. So 1, 2, 3, 4, 5 over 1. 1, 2, 3, 4, 5 over 1. Okay, I've got a graph doing something like that, right? Now, these values, as x approaches 3, is going to be off my grid here, but I do know that there's some point up here. So when x is 3, we're looking at that, okay? So, according to our limit definition, here's what we're asking ourselves. As x approaches 3 from the left side, and as x approaches 3 from the right side, do we get a single, specific, unique output on our graph? Well, okay, so that would mean that I'm following along with this, that, all right, well, as we approach from the left, okay, I'm following this graph up to this point. As I approach from the right, I'm following the graph down to here. Oh, I get a value. And that value right here should be 12. Okay? Now, at the same time, I would come over to my table of values, and I'm not going to put all of these in here, but I'm wanting to look around 3. I know that I want to look around 3 because the problem tells me 3. And if I put 3 in here, and I just literally plug 3 in, do the algebra, I get a 12. So now the only question in my mind is, what's going on around 3? So if I start taking a look at the values surrounding 3, like 2.99, 2.98, 2.97, okay? 3.01, 3.02, 3.03. What is happening when I look at my table of values on my calculator to these numbers? I'm going to expect right now, I'm not doing the work, but I'm going to expect something like this is an 11.999 or something like that. Okay, maybe this is an 11.998. Maybe this is an 11.99. I don't know. It could also round to an 8. I don't know, but I would bet if I'm looking at my calculator that these values are counting up getting closer to 12. So what I'm going to expect to see happening here is like 12.0001, something like that. Right over 12. Okay, maybe a little bit bigger than the one before. Well, not maybe, it would have to be. Okay, because it's linear. So what we're looking at here is as we're approaching 3 from the right, which would be over here, and 3 from the left. So this would be from the left side. The numbers are getting bigger. 3 from the right, the numbers are getting smaller, so we're coming this way. What do we get out? 12. Okay? Now this problem was a little easier because it's linear. As we keep going, they get a little bit more challenging. So, what I would like you guys to do now is to take a look at 2, 3, and 4. Because what's going to start happening on 2, 3, and 4 is I can't just plug the number in. This one worked out that I could have just plugged 3 into the problem because it's linear, and I got out 12 right away. That won't always be the case. So, for 2, 3, and 4, please take your graphing calculators, look at a table, look at a graph, and can you determine the limit?